Hello there and welcome back to this video series on control systems. Over the past few videos, we have been seeing topics on modeling such as classification of control systems, what are LTI systems, transfer functions, and then simplifying block diagrams to find the transfer function, signal flow graphs, and Mason's gain formula. From now on, we'll see a few topics on analysis and then subsequently design of control systems to meet certain specifications. In this video, we'll try to see something about the need for time response analysis and what are some test signals that are used. When we say time response analysis, this involves studying the mathematical model of a system and then try to evaluate several what-if scenarios. We note that studying a mathematical model of the system is easier, quicker, and cheaper than studying the system itself. You don't have to build the hardware, then test and evaluate the output. On a mathematical model, you can evaluate several what-if scenarios. This act of performing computations using the mathematical model to assess the performance of a system is called simulation. The results of this simulation can be used to intelligently guess the performance of the system, and also if there are two systems, you can study the results of simulation and infer from them as to which one is actually a better system, and then we'll build that better system. This will save a lot of time, effort, and money. Studying this mathematical model is especially useful because we can take the mathematical model of a system and subject that system to several inputs and see several situations in which the system may or may not fail. And this topic on time response analysis involves studying the response of different categories of systems when they are subjected to some of the tough inputs, the inputs which may have damaging effect on the system, which may have effect on the accuracy and precision of the system. We will consider several standard test inputs which we use in mathematical model to study the performance of the system. One of the first inputs that we study is an impulse input. An impulse input is defined as shown over here mathematically. When TO tends to 0 here, A over TO tends to be very high. So we are considering a small pulse which is very high in a very short period of time. This may look very confusing to begin with, but notice that its Laplace transform is really very simple. Its Laplace transform is A. Okay. Later we will see that if A is equal to 1, we call it unit impulse input. Unit impulse input is shown in the graph here. It's a very thin and very tall pulse whose area is A. Okay, in this case we say we want to have the area to be 5. A second input that we consider is a step input, a sudden and persistent change. That is, a change occurs and the change continues to remain at a point. That is what we call step input. And mathematically, we will represent step input as gt is equal to 0 when time t is less than 0, a otherwise. This a is the magnitude of the step input. Later, we say that when a is equal to 1, it is unit step input. Examples of this step input include suddenly opening a valve and keeping it open at that position. So when you keep it at that position, outflow or inflow remains constant. Similarly, suddenly pressing on the acceleration pedal and keeping it there, that will also be a step input. A step input is represented in a picture as shown here. Along x-axis you have time, along y-axis you have magnitude of the input signal, and this red line indicates step input. Here the magnitude of the step input A is 5. When A is equal to 1, we call it unit step input. Another input is a ramp input, which is a sudden and uniformly increasing. So in the case of step, it is sudden and remains constant after the change happened. Whereas in the case of ramp input, sudden and uniformly increasing. We'll see a picture of it as shown here. Ramp input for y, A is equal to 5. You can see time t is equal to 2. It is 2 times 5. 4 times 5. 6 times 5. Then so on. 8 times 5. That is, output is A times time. Along x-axis you have time, along y-axis you have input. To study the response of the system to much faster inputs, faster than ramp inputs, parabolic input is used. Mathematically, parabolic input you represent by at square over 2, and its Laplace transform is a over s cube. And parabolic input, you can see here, it's very rapidly increasing. In a very short time, it can become very large. To study the performance of the system when it is subjected to consistently changing input, fluctuating input, we use a sinusoidal input. Sinusoidal input is given here, where A is the magnitude of the sinusoid, and we say that when A is equal to 1, it is a unit sinusoid. Omega is the frequency of the sinusoid, how fast it is changing. Sinusoid input is shown here. A is equal to 5, you can see the magnitude peaks at 5. A is equal to 1, we call it a unit sinusoid. As mentioned already, if A is equal to 1, these inputs are termed as unit inputs. So when A is equal to 1, it is unit impulse input represented by Ui. When A is equal to 1 in a step input, it is unit step input represented by Us, unit ramp input represented by Ur, unit parabolic input represented by Up, and unit sinusoidal input represented by U sin. We note their Laplace transforms. Of unit impulse input is 1, unit step input is 1 over s, ramp input is 1 over s square, parabolic input is 1 over s cube, and sinusoidal input Laplace transform is omega over s square plus omega square. I would strongly suggest that you remember these and also review Laplace transform topics given on videos 0, 5, 6, 7, 8 and 9. And thus, to summarize, we can say that simulation means computationally predicting the output of the system under various conditions, and several test signals are used in simulation in our syllabus: unit impulse input, unit step input, unit ramp input, parabolic input, and sinusoidal input. I think that's all we have for now. Have a great day.